Now we'll see the new part, angular deformation. We have already talked about the linear deformation. Now the remaining part is the angular deformation. So in the case of the angular deformation, you think at the time t, there was at time, any instant of time, one fluid element we are choosing here like this. So what is the fluid element? We are choosing A, B, C. The one rectangular fluid element we are choosing at time t, at any instant of time. So after delta t time, after the delta t time, you see the fluid element as it is under continuous deformation. As shear stress is acting over it, it becomes in this way, in this manner. B dash, B dash, C dash. As shear stress is acting over it, under continuous deformation after a certain time delta t, it looks like in this way. Okay. So this analysis, what is the strain rate we have to calculate? How much deformation is taking place here? Because simply you are seeing there is an angular deformation. How it is angular deformation? Because here you see the angular change. Previously, the AC and AB are perpendicular. This AC and AB, this part were perpendicular to each other at t time. At t. But after t plus delta t, at the time t plus delta t time, this is no more a perpendicular. Some angular change is occurring in between this. Some angular change has been occurring in between this. You see here, some angular changes has been occurring. So what is the angular change here? That is the delta theta. Previously it was in horizontal condition AB, but now change is delta theta, angle change. Here how much change? Delta beta, let you take. Or delta alpha, better to write it, delta alpha beta we are writing in terms. So delta alpha, delta beta. Previously it was horizontal. Now angular change is occurring, delta alpha. Okay, delta alpha in anti-clockwise direction. See, from horizontal to in this direction. So it is anti-clockwise direction, counterclockwise direction, and delta beta occurs at delta t time in clockwise direction. Previously it was vertical, now it is like this. Okay. So that much angle change is occurring. So rate of change of angle. What is the rate of change of angle? Delta t. On that case, other case. That is the rate of change of angle. So it is as alpha dot. It is as the rate of change of angle. Why rate consideration we are taking? Because rate consideration is taking as here is the fluid. Whenever under in the motion condition, it is continuous deform. That's why the rate term we are talking about. So what is the total deformation? Previously, about AC and BC, AB and AC, the angle was 90 degrees. Previous angle was perpendicular. It was. Now how much angle change? This now at delta t time, what is the change? Angular change, angular deformation, how much? The angular deformation is del alpha plus del. That is the angular deformation. That is the angle change. Whatever total angle change, previously it was 90, now it is moving along counterclockwise, it is moving along clockwise. So net angle change in angle, 90 minus del alpha, del beta. Now this angle is 90 minus, previously it was 90, now it is 90 minus this. So change is this plus this, del alpha plus del. There is a change. So rate of change of angular deformation. Rate of change of angular deformation means delta t. That is the rate of change of angular deformation. That is the rate of change of angular deformation. So better to write it down. Alpha dot plus beta. Better to write it down. This is alpha dot plus beta. Okay. So that is the angular change, alpha dot plus beta. Now we have to go for searching what is alpha dot, what is beta. The concept I am giving it in this way. So rate of angular change is alpha dot plus beta. This element is changing del alpha by del t. This element is changing alpha by del. That's all about here. So we again rewrite this thing. Try to understand. So again, A, B, C, S, yes, CS. So this is the coordinate system wise, this is the x direction, top is the y direction. No doubt about it. So along x direction velocity is u, along y direction velocity is this AB is delta x, AC is delta y. At AC, the velocity is u. At AC, the velocity is u. Okay. At AC, the velocity is u may be the function of x and y. U is the function of x and y. How it is a function of x and y? How it is a y? Because you see, and v is also a function of x and y. If you're considering this thing, previously it was like this way. Previously it was like this way. Take it b double dash. So it is the delta x. It is a roughly delta x. But b should have come here, but instead of here, it is deviated in this portion. It is some deviation is all. So if you go along x-axis, some vertical changes came. So along y-axis, velocity is the v. So at here, if the velocity is the v vertically, here the velocity at a point, the vertical velocity, if it is a v, here the velocity becomes v plus del v del x plus higher order terms. Because v is changing at a, what is the velocity, vertical velocity along y-axis velocity? Here the velocity is different because as it is the along, it is changing with the del x. That's why this move is occurring at delta t time. So displacement is this. Velocity into time will gives you the displacement. So B dash, B double dash is coming in this way. The total. Sorry, this I'm telling it here. So here, sorry, here it is not. It is a total. It's not this much. This much is only that portion. This BB dash is only this portion, and V is remaining portion. Here is the V delta T. So total is coming as a, this is the V delta T, because vertical displacement how much here? Here vertical displacement is V into delta T. V into delta T. Vertical displacement of point A. Point B vertical displacement is total this much. That is a total. From here to here, point B previously at in this location, now it is the displacement is this much. Out of here is the VT and remaining part is this much into higher order terms. So B dash, B double dash is del V del X dx plus higher order terms into delta T. That is the function. Similar way, from here to here, it is U delta T. After delta T time, it is displacement is velocity U and delta T. But here you see the same way if you do this thing, the C point moves more than the A point. C point moves more here than the A point. C point moves here. So this much is del U, del T, and the total if you consider here. So there is a variation of the U with respect to Y direction. So U variation is there with respect to Y direction. So here V variation along x-axis. Along x-axis if you give, the V variation is there. Along y-axis if you go, the U variation is there. So U is varying with the Y, V is varying with X. Same way, C double dash also. So C dash, C double dash will gives you du dy ly plus dot dot dot. Now if you take the 10 del alpha. So 10 del alpha will gives you in this triangle B dash B double dash by A. So A B double dash is nearly equal to the del X. We are not going such a changes. So del V del X into dx plus higher order terms. Higher order terms means del X square by 2 factorial, del X cube by 3 factorial in this way over the term. Delta T divided by del X. Consideration is del alpha if it is a very small quantity. Very small. Angle is very small. So tan del alpha be equal to the del alpha. So it can be written as the del alpha is equal to the center. If you take the delta T in this side, delta T, so it will gives you. Now if you do the limiting parameter, if you limit delta T tends to 0. If you make it the limit, so if delta T tends to 0, delta X, delta Y, everything will be tends to 0. This is will be cancelled out, but the higher order terms all become 0. So only remaining part will be del V del X. So alpha dot is equal to del V del X. So this alpha dot is equal to del V del X, no doubt. Same way, if you take tan del beta, so it will gives you C dash C double dash, C dash C double dash divided by del Y. So it will gives you the del U del Y is equal to beta dot. Same one, same manner. Beta dot will gives you del U del Y. So alpha dot beta dot you are getting. So total angular deformation. So total angular deformation, we'll see it here. We're rewriting this thing. The angular deformation is a two-dimensional only considering alpha dot plus beta dot. So alpha dot is del V del X, del U, del Y. No doubt about it. There is a no doubt regarding this. The same way, if you think U, if I write U1, V, if I write U2, and X, if I write X1, and Y, if I write X2. Okay. But before telling this thing, I'm telling it here, this is the thing. It is denoted as the deformation. So gamma X, gamma X. That is a total deformation. There is a total deformation. So how we are writing it, this thing, I'm just telling you, is a del U2 del X1, del U1. You see the opposite here. What is the opposite? So it can be better to write del Uj del Xi. Sorry. Now we are written. So del Uy is the indices form, we can write it. So E of Ij. So it is better to write it E of Ij is equal to del Ui del Xj plus del Uj. If I is equal to 1 and j is equal to 3, that means x and 1 z coordinate. How it will be right that? That is the easiness of this to getting this. So in that case, del 1 3 will gives you del 1 I del x3 del u3 x. If the coordinate is 1 and 3 in such cases. So it is better to another way is the indices form. Indices form is easier, generalized. So du del z plus del w del w is u3, z is in this manner we can write any equation we can write it in this manner. That is the angular deformation. This way we can write it. 2 3 gamma 2 3 also we can write it down. So gamma 1 2 gamma 2 3 gamma 1 3 all we can write it down. And we can see one more thing. See here, I'm telling. So del 1 3 we are writing it down. 1 del x3 del 3 x. same way. T1 X3. You see, these are the same. So cross shear strain component also are the same one. So this is where. Just like we are writing it, tau yj is equal to tau ji, shear stress component. Similarly, the strain component also will be the same. That is the concept. Now the concept is come the angular velocity. Angular velocity you can say in this way. Just after this thing, we are doing the angular velocity concept. What is the velocity? We seen the rate of angular deformation. We have seen it here. Angular velocity you see here, it is the moving how much? This is alpha dot, rate of change. Here rate of change is the beta dot. But alpha dot is the counterclockwise. Beta dot is the clockwise. So alpha dot is the counterclockwise, beta dot is the clockwise. Angular velocity in these two-dimensional cases is the mean of alpha dot minus beta dot. Mean value. What is the mean value? Why beta is the negative term coming? Because it is a clockwise. It is the counterclockwise. We are taking counterclockwise as a positive, counterclockwise as a negative. So half alpha dot minus beta dot will give you the angular velocity about which axis? It's a xy plane. So whether it is rotating about z axis, always perpendicular to the plane. So this is the W omega z. So omega z is the angular velocity about z will gives you same value alpha dot. If you remember, del v del x minus del u. That's the omega. This way we can write it down in this kind of the equation. So this is about angular velocity. Angular velocity, we have defined the mean of the rate of angular deformation. You have to consider the sign convention here. You have to consider the sign convention here. So about z axis. So or omega is a xy plane. About z axis xy. The same manner you can do it. Now one concept I am taking, the vorticity concept. Vorticity concept we are taking. Some vector we'll see the vorticity concept. It will gives you the better understanding of the angular deformation concept. Why vorticity is coming? Vorticity is giving the rotationality of the flow. Rotationality of the flow means in a flow, if you give one this kind of the thing, jet type of the thing, particle, if you choose the flow, after some part you see as it is the flow is the rotationality is there, so the orientation will be changed in this. So that means the flow, as we give the flow, the orientation of this matter is changing here. So then we can say the flow is the rotational flow. There must be some rotation. Rotational flow. How to define the rotational flow? The rotational flow is defining is the curl V. The rotationality is defined by curl V. This is known as the vorticity vector. Capital omega is the vorticity vector. The curl V, curl operation of V is the vorticity vector. It gives the rotationality of the flow. So if the flow is not rotating, that means it will be a null vector. Vorticity vector will be a null vector. Then we can say the flow is a irrotational flow. What is the condition to become the flow rotational flow? The condition to become rotational flow is there must be the presence of the curl of velocity. Curl of velocity. This thing we will consider now one by one. One case of the pure rotation, we will discuss about this thing. Yes, okay. First we discuss this thing. The pure rotation, then we will come to the vorticity. Pure rotation, if you see, it looks like a pure rotation. The element is purely rotating. What is the condition? Rotation condition, if you think that, so in two-dimensional cases, omega z is equal to half into del v del x minus del u del y. Condition, I am writing the condition, just writing the condition is del v del x is equal to minus du du. Or vice versa. Or vice versa. So del v del x, both are magnitude is the same in magnitude. Magnitude is the same, and direction also same. Because previously in case we see del v del x we are considering in this direction, clockwise, counterclockwise direction, and del u del y we are taking the clockwise direction. If both are the same in direction, so element is purely rotating. Element is purely rotating and not equal to 0. But if you take del del y, so it is du dy plus dv dx. That is becomes 0. So no deformation, no angular deformation, only rotation. This is 0, no angular deformation, because del v del x is equal to minus du dy. So it becomes 0. So no angular deformation, only there is rotation. That is called the pure rotation case. So pure rotation condition is the condition for the pure rotation is del v del x is equal to minus del u del y. Previously both are opposite in sense rotation, now both are same in sense. Now both are same in sense of rotation. That is the pure rotation. No rotation or irrotational flow. Irrotational flow. Irrotational flow is that wz is equal to 0. Angular velocity is 0. So hence dv dx is equal to du. That is a condition. Both are magnitude is the same and direction is the opposite. Because del v del x is the counterclockwise same direction, it is the clockwise same direction. Both same magnitude, but the direction of is the opposite. Then in that case we can say it is a irrotational flow. So irrotational flow, no rotation, but angular deformation must be there. Angular deformation will be 2 du dy or 2 dv dx, anything. Del v del x. That is the irrotational case. So two cases we can derive from the previous equation.